All right, so our first sample problems we had were Bronsted-Lowry reactions that we were to complete. But before we get to those, I want to do a little introduction, I guess, on the term proton, which is kind of thrown around a little bit with their Bronsted-Lowry definition. So, from our grade 10 science and grade 11 chemistry knowledge, what we'll remember is that a hydrogen atom, because it is element number one on the periodic table, that means that it has one proton. And as an atom, we know atoms are electrically neutral, which means that protons and electrons have to be equal. So there's one proton and one electron. In terms of neutrons, neutrons is the topic touched on in grade 11. And when we look at the mass number of a hydrogen atom, the most common mass number is a mass number of 1, right? The atomic number is 1.01, which means that the mass number of 1 has to be the sum of protons and neutrons. So because we know that a hydrogen atom is one proton, that means that most hydrogen atoms have 0 neutrons. So that's the makeup of subatomic particles for a hydrogen atom. One proton, one electron, and 0 neutrons. As an ion, and a hydrogen ion is H positive. Remember, what a positive means is that there's one more proton than we have electrons. So it's still hydrogen, which means that it's still one proton, but because it has a net charge of one positive, that means that it has lost its electron. So now 0 electrons and 0 neutrons. So what that means is that a hydrogen ion, so H positive, is really just one proton. Because if we look at the particle makeup of it, that's all it is. So when you hear the term thrown around that it's Bronsted-Lowry acid is a proton donor, that just means that it is a hydrogen ion donor. Or a Bronsted-Lowry base is a proton acceptor, that just means it's a hydrogen ion acceptor. So just so you're clear with where those terms come from. So if we look at our 3 sample questions, what we're asked to do here is we're asked to predict our products. We're asked to label each substance as an acid or base, and we're going to identify each conjugate acid-base pair. So our first order of business is to look at our starting materials and determine which one of these substances would be most likely to donate a proton, and which one of these substances would be most likely to accept a proton, or a hydrogen ion. So water is a substance, and you'll see this as we go through more questions, but you'll see that water can be an acceptor in some cases and a base in other cases. Right? Just depending on what it reacts with. So here we're reacting with CH3COOH. So based on the knowledge that we've done so far in this course, right, in grade 11 chemistry, you may recognize that COOH at the end. So in our organic section, we talked about carboxylic acids. And then in grade 11, we just said that some acids will end in COOH. So that's something that we should recognize a little bit. So when we see that COOH ending, we're going to deem that substance to be an acid. So when we talk about acids, we're looking for substances that have hydrogens to donate. So if this is an acid, that means that water is going to act as a base in this case. So again, water is amphiprotic, an acid in some cases and a base in others. So when we do these acid-base reactions, we want to make sure we continue to show our reactions at equilibrium. So we draw those double arrows. And we're going to say, according to definition, is that our proton is going to move from our acid toward our base. So our proton is going to move in this direction. So what we're going to say is, for our products, we want to predict what CH3COOH looks like after it gives up a hydrogen ion. So in this case, I really wouldn't mark it wrong in either case, but we should show the hydrogen off the end coming, because the one that's attached to the oxygen is the substance that's going to be donated. So we're going to say here that it's the same substance but without that hydrogen at the end. So CH3, CO, and we need to be careful of our state of matter. It was neutral, it just lost a positive, which means that it should be negatively charged. Just be careful of that. State of matter should be aqueous, and the ion is going to be aqueous in solution. Then we're going to say, what does water become after it gains a proton? So it was H2O, it just gained a hydrogen, so it becomes H3O, and it was neutral, it had no charge, and it gained a positive, so now this becomes positively charged. So there are our products, and it's an ion, so it's going to be aqueous. The other thing we have to be careful of is just our net charge, and it's kind of a tripping point for some students, so just make sure that your net charge on the left is the same as the net charge on the right. So neutral and neutral, net charge of 0 on the left, 1 negative, 1 positive, and net charge of 0 on the right. So now what we want to do is we want to identify these substances as being acids or bases. So what we have to do is we have to look at the reverse process. Say, how does CH3COO negative form CH3COOH? Well, we'll have to accept a hydrogen. And same thing here, H3O positive becomes H2O by donating hydrogen. So our hydrogen is going to move in this direction, in this case. And by definition, this is donating a proton, so that should be an acid. And this is accepting a proton, that should be a base. So second part is done. We've labeled every substance as an acid or a base. So the next thing we want to do is we want to label every substance as being, or in terms of its conjugate pair. So with a conjugate pair, what that just means is two substances that differ by a proton. So we would say if our acetic acid, so CH3COOH, is our acid, its conjugate pair or its conjugate base is going to be what it looks like after it gives up a proton. So we would say that would be a conjugate pair, CH3COOH and CH3COO negative. And then our second conjugate pair is going to be H2O and H3O positive. So those are our two conjugate pairs. So for conjugate pairs, we should always have one substance on the left and one substance on the right. It'll always be one acid and one base. So there's our first reaction. For question B. So question B is HNO3 plus OH negative. So again, first order of business is we want to try to determine which of our substances is going to act like an acid and which of our substances is going to act like a base. So again, different ways to look at it. A grade 11 way of looking at things, so the Arrhenius definition, starts with hydrogen or ends at COH, is usually a good telling point that it's going to be an acid. The other idea is that this OH negative ion, so our hydroxide ion, you would expect that negatively charged substances would want to attract positives because we know opposites attract. So this would make it a good base. So we're going to label this a base, and we'll label this as an acid. So it starts with hydrogen, we'd expect it would donate. That means proton is going to move in this direction. So equilibrium arrows, which we want to include. And then we're going to say, what do we get when we donate our proton? So HNO3 is going to donate a proton. So we're saying, what is HNO3 after it lost a hydrogen? Well, there's no more hydrogen, so it's going to be NO3. It was neutral and lost a positive, and it's going to become negative. And negative ions, or any ions, are aqueous. Second substance, OH negative, accepted a positively charged hydrogen. So we had one oxygen, one hydrogen. We now have two hydrogens. So something we become comfortable with is you'll start to see that OH negative, when it accepts, becomes H2O. It was negative, became positive, it's now neutral. And we're going to write this as being a liquid. So I'm going to put an L there. We don't write that water as aqueous because that's being redundant. Right? Aqueous means it's dissolved in water. So net charge on the left is 1 negative, net charge on the right is 1 negative. We want to look at the reverse process. So how does NO3 negative form HNO3? Well, it's going to accept, and water is going to donate. So we'll show the proton moving. Sorry about that. So we are going to show the proton moving from our H2O to our NO3 negative. So proton moving in this direction, and by definition, proton donator is going to be an acid, and proton acceptor is going to be a base. And then the last thing is we want to label our pairs. Again, we want to make sure the two substances differ by a proton, so we would say that HNO3 would be 1, and then its conjugate base is going to be NO3 negative. So there's one pair, second pair, OH negative, and H2O. What you'll notice, and again I mentioned this earlier, is that water in some cases acts like a base, as it does in question A, whereas question B, it acts like an acid. So that is one of the substances we call amphiprotic or amphoteric. So there is question A and B, which brings us to our last question, question C. So HS negative and H2O. Now this one is a little bit tricky. The reason this one's a little bit tricky is because there's two ways of doing it. We just talked about how water can be amphiprotic, so it accepts and sometimes it donates others. HS negative is the same idea. So here, it starts with hydrogen, so it has one to donate. It can be an acid, but also negatively charged, which means it can accept. So that means it could be a base. So what we can show is both cases. So in this case, I would accept either answer. So we're going to show both cases. So both cases is going to be, in some cases, HS negative is going to donate to water. So we show our hydrogen ion moving in that direction. If that's the case, then what we should get is HS negative after it donates. There's no more hydrogen, so it's just S. It was negative, and it became charge of 2 negative. So it was negative, it lost another positive, so it becomes 2 negative. It's an ion, so it's going to be aqueous. Water accepts, so it was H2O, now it becomes H3O. And again, that's an ion, so it's going to be aqueous. So here are our products. Just check your charges. Net charge of 1 negative on the left, a charge of 1 negative on the right, and proton would move in this direction for the reverse reaction. So we can label this as being proton donor, proton acceptor, and proton donor. So there's our first example. And again, there's two ways of doing it, so we'll get to the second here in a minute. So in terms of our conjugate pairs, they differ by a proton. So it's HS negative and its conjugate base is S2 negative, whereas H2O and H3O positive would be our second conjugate pair. So there's one example. The second example would be if the two substances act in the opposite way. So instead of HS negative donating here, we would say HS negative is going to accept. So if that was the case, we would say HS negative plus H2O equilibrium arrows. So now we're showing the proton going in this direction. So HS negative is going to accept the proton. So had one hydrogen is now going to have two hydrogens, so it's H2S. This net charge was negative. It gained a positive, so that means it's going to become neutral. The acids are aqueous. And H2O donates, so it's going to form OH negative. Net charge of 1 negative on the left, net charge of 1 negative on the right, so we're good there. Reverse process, H2S forms HS negative by donating. So protons should move in this direction, which allows us to label. So proton acceptor, proton donator or donor, proton donor, proton acceptor. And the last order of business is to couple them up. So there's its base and there's its conjugate acid. Again, differ by a proton. And then our second pair, H2O and OH negative. So as we go through these, what you really have to be careful of is your net charge, not your net charge, but your charge in the individual, and you can use your net charge to check on that. Make sure that you have your equilibrium arrows, make sure you put your states of matter, so all those little details really come in handy here.